Hi guys, can you guys hear me?
I can hear you.
Okay, I'm going to wait a few more minutes and then get started. Okay. I'm going to start today's lecture. We're going to move on to chapter 17. In chapter 17, we will learn about some additional aspects of aqueous equilibria. This chapter is an extension of those in chapter 16. So in chapter 16, we've learned about weak acid or weak base in aqueous solution. And we've also learned about ionic compound, salts in aqueous solution. So chapter 16, we learn about acid and base in aqueous solution. We also learn about ionic compound, salts in aqueous solution. Now we will learn about a little bit more complex situation where we have weak acid and soluble salt of that acid mixed together in aqueous solution. Okay, so we have weak acid and soluble mixed together in aqueous solution. Okay, this is what we're going to um, learn today. So let's say the weak acid is acetic acid, and the soluble salt of that acid is sodium acetate. Okay, so the weak acid is acetic acid. The salt of that acid is sodium acetate. The acetic acid and sodium acetate, if you mix them together, they will not have any chemical reactions with each other. I'm going to repeat that. When you mix acetic acid and sodium acetate together in a flask, they will not have any chemical reactions with each other. But the resulting product from each ionization will have an effect in final aqueous solution. So in order to know what effect this mixture is going to have, we need to find out how a so in order to know what effect this mixture is going to have, if the screen is blurry, can you guys please let me know? So in order to know the effect this mixture is going to have, we need to find out how acetic acid and sodium acetate each behaves in aqueous solution. Okay, so for acetic acid, since it's a weak acid, we know that this would only partially ionize in aqueous solution, right? We've learned that in chapter 16. So we can represent this by dynamic equilibrium expression using this double arrow. For sodium acetate, this is a soluble ionic compound and a strong electrolyte. Okay, again, if you want to know whether this is soluble ionic compound or not, please go back to the ionic compound solubility table in chapter 16 lecture slide. And since this is a strong electrolyte, it will dissociate completely in an aqueous solution and remain in ionized forms, sodium cation and acetate anion. And therefore, we use one arrow to indicate the complete dissociation of this strong electrolyte. So then what happens is, okay, so again, if the screen is blurry, let me know, okay? So then what happens is due to the complete ionization of the sodium acetate, which increases the acetate anion concentration within the system, the equilibrium concentration of acetic acid dissociation equation is going to be shifted. Okay. So due to this, due to the complete ionization of sodium acetate, which increases the acetate anion concentration within the equilibrium concentration of acetic acid dissociation equation is going to be shifted. So which direction this equation is going to be shifted? The moment you mix acetic acid and sodium acetate together in a flask, sodium acetate will immediately dissociate in ionic forms. The sodium acetate will immediately become sodium cation and acetate anion, right? So that in the flask you will have acetic acid with increased concentration of acetic acid from the sodium acetate. In chapter 15, according to Le Chatelier's principle, according to this principle, if we add a component to an equilibrium system, the equilibrium will shift to a direction to consume that added component, right? So in this case, the system will think that we have increased the concentration of acetate anion. From where? From the ionization of sodium acetate. So then, because the system thinks that we have increased or we have added the concentration of the acetate anion, the equilibrium will shift to left because and therefore the uh, why is it going to shift to left? because this now equilibrium system would want to consume the increased concentration of the acetate anion, okay, according to Le Chatelier's principle. So then if the reaction shift to the left, it's going to consume the high increased concentration of acetate anion. But then what's going to happen to the proton concentration? The proton concentration will now decrease. Okay. So in other words, the presence of added acetate anion cause the acetic acid to ionize less than normally it would normally would. Okay. The acetate anion is called common ion. The common ion is suppressing the ionization of acetic acid. I'm going to summarize that here. Presence of added or increased acid caused the reaction shift left. Okay, because the reaction is shift to the left, acetic acid would ionize less than it would normally do, causing acetic acid to less than okay, and then this in other words, we can say that this acetate anion is suppressing the ionization of acetic acid. Okay, acetic this acetate anion here, this is called common. Why? Because salt form of that acid. Okay, this is the common ion. So here is the summary for the previous observation. Whenever a weak electrolyte, what was a weak electrolyte? Acetic acid. Whenever weak electrolyte and strong electrolyte, what was strong electrolyte? Sodium acetate. Whenever weak electrolyte and strong electrolyte containing a common ion, what's a common ion? Acetate, right? Whenever weak electrolyte and strong electrolyte containing a common ion are placed together in an aqueous solution, the weak electrolyte, acetic acid, ionizes less than it would if it were alone in the solution. Okay. Let's try a sample exercise to get a better idea.
Dr. Lee, sorry to cut you off. Could you go back,
Oh,
please?
yeah.
Thank you.
Let me know when you're done.
I'm done, thank you.
All right. I'm going to read the question. What is the pH of a solution made by adding 0.3 mole of acetic acid and zero point 0.3 mole of sodium acetate to enough water to make 1 liter of solution? Okay, so this question is about mixing acetic acid and soluble salt of that acid, which is sodium acetate. Okay, so we immediately know that the common ion is acetate, right? In order to determine the pH, in order to determine the pH of the solution, we need to find out the proton concentration in the mixture. As we, so we need to find proton concentration. As we observed from the previous slide, we know what mixing these two components will result, right? Mixing these two components will result in lowering the proton concentration um, compared to when acetic acid is dissociating alone, right? So let's try to find the proton concentration. I'm going to start by writing an equilibrium reaction of the acetic acid. The proton concentration can be found from the equilibrium constant expression for this equation, which is if we know this, we can find the pH, right? So let's make a table to organize the information that we know and the information that we don't know. Okay, so initial change equilibrium. The initial concentration of acetic acid is already given. Okay, it's 0 0.3 mole in 1 liter, so we know that it's 0 0.3 molar. Okay, and then the initial concentration of proton is 0 to start. Okay, we don't have any proton in the system yet. However, the initial concentration of acetate is actually the concentration of dissociated sodium acetate. Okay, so the dissociation of sodium acetate will be responsible for this concentration of the acetate anion. Okay, because you had 0 0.3 mole of sodium acetate, you also have 0 0.3 mole of this acetate anion to start off. Okay, then let's use X to denote the change in concentration. Okay, so X, according to the reaction stoichiometry, the change is going to be XXX. As for the sign, okay, you are depleting the reactant, so you have negative X for the change in acetic acid. You are generating the product, so you're putting positive sign for the products that you're generating. Then the equilibrium concentration would be 0 0.3 molar minus X, and then 0 0.3 molar plus X. So if we plug in the equilibrium expression in terms of X, again, as we did in chapter 16, we will assume that this X is very, very small. And it's going to be even smaller now, right? Because now we know that for the weak acid dissociation, we know that the proton concentration is pretty low, but now that we have sodium acetate hindering the dissociation, we know that this concentration is going to be even lower now. Okay, so we're going to assume that this is very, very small. So um, we're going to uh, disregard or neglect the amount of X in the equilibrium concentration of the acid. Okay. Again, we're going to neglect the X. Okay. So to make it more clear, we will ignore adding of the extremely small value of X into the 0.3 molar of acetic acid and 0.3 molar of the acetate. Okay, we're going to ignore adding of this extremely small value into the concentration of acetic acid and the acetate. Okay, so then let's plug this into the Ka expression. The proton concentration, uh, this is going to be X, and then acetate concentration is 0.3, acetic acid concentration is 0.3. Okay, and what is the Ka value? Okay, so according to the table 16.2 from chapter 16, we know that the Ka, the acid dissociation constant of acetic acid, is going to be this value. Okay, so we know that the Ka of this acetic acid is 1.8 times 10 to the negative 5. If we solve for X, X is basically 1.8 times 10 to the negative 5. Okay, so now that what is X? X is a proton concentration, right? The whole purpose of this question was to find pH of the solution. Now that we have proton concentration, can you find the pH? You just have to take the negative log of the concentration of proton. So now the pH is going to be negative log of X, which is negative log of proton concentration, right? Negative log of 10, negative log of 1.8 times 10 to the negative 5 equals to 4.74. So 4.74 is going to be the pH of a solution made by adding this amount of acetic acid and this amount of sodium acetate together.
Dr. Lee, I have a question.
Yes.
Will this chart be provided for us on the exam, or do we have to memorize this?
Oh, you don't have to memorize any of the Ka value.
Okay, thank you.
Mhm. Okay, so just keep in mind that when you are doing this, when you're adding weak acid and salt form of that acid together in an aqueous solution, what's going to happen is that the 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 reaction is going to shift to the left. It will hinder the dissociation of this acetic acid. The proton concentration is going to be lower than when acetic acid is dissociating in the aqueous solution by itself without sodium acetate. Okay. let me further explain this. So the the this question that we just solved, it was a zero point 0.3 mole solution of acetic acid. Okay, the pH of this solution when it's by itself is 2.64. This corresponds to proton concentration of 2.3 times 10 to the negative 3 molar. But in this question that we just solved, you had 0.3 molar of acetic acid, but you had 0.3 molar of sodium acetate as well. Okay, so then what happened was the pH value was 4.74, which correspond to proton concentration of 1.8 times 10 to the negative 5. As you can see from the numerical value comparison, oh, not molar. As you can see, proton concentration in this situation is way, way lower than when acetic acid was dissociating alone, right? So yeah, there's a comparison. So the common ion effect, you want me to
Dr.
go
Lee?
you want me to go back?
Yeah, just real quick.
Yeah.
Thank you.
Here or the previous slide?
That's it. I'm good. Thank you.
Okay.
I appreciate it.
Okay. So the common ion effect applies to weak bases in the same way. Okay. If a solution contains weak base such as ammonia, this is a weak base, right? If the solution contains a weak base such as ammonia, for an example, and if it is mixed with salt of its conjugate acid, salt of its conjugate uh, acid such as ammonium chloride. Okay. Then, due to the common ion NH4 plus, this is a common ion, the base won't dissociate as much as when it is alone in the solution. Very similar to the acetic acid situation that we've just observed. Okay, so in this case, instead of decreasing the proton concentration, what happens here is that hydroxide concentration will be lower compared to when ammonia is dissociating by itself. Okay. This is the salt of mm, lowering the hydroxide concentration. Okay, this is the common ion. So you can also observe the common ion effect in weak base and salt of its conjugate acid mixture. Now let's move on to talk about buffers. Okay, buffers is a solution of mixture of high concentration of weak conjugate acid-base pair. Okay. Buffer is a solution mixture of high concentration of weak acid, conjugate acid, base pair. Okay, so what happens to this buffer solution is when you add small amount of strong acid or strong base into this buffer solutions. So a buffer solution will contain this, okay? And if you add strong acid or if you add strong base, small amount though, very small amount. If you add small amount of strong acid or strong base into these buffer solutions, the buffer solution will resist drastic changes in pH. Okay? It will resist drastic changes in pH. The purpose of buffer solution is to maintain constant pH level throughout the solution. Okay? So the purpose of buffer solution is to maintain constant pH level throughout solution. Okay. Example of a buffer. Mixture of a weak conjugate acid base pair, right? So a mixture of this or mixture of this or mixture of this. So a mixture of hydrofluoric acid and fluoride, or mixture of acetic acid, acetate, mixture of hydrocyanic acid or cyanide. These are all examples of buffer solution. Okay. The real life example of buffer solution is human blood and seawater. So human blood is a very complex buffer solution that maintains pH around 7.4. And seawater is also a buffer solution that maintains pH around 8.1 to 8.3. Okay, so without being buffered, these solutions will fluctuate in pH levels and then it will cause serious problems to human health and the living organisms in the seawater. Okay, so in order to make the buffer,
Dr. Lee, sorry, I have a question.
you want me to go back?
I just have a question. Are buffers always neutral or slightly alkaline?
It's going to be very close to the neutral pH value.
Okay, thank you.
Mhm. So in order to make buffer, number one, you can mix weak acid and salt of its conjugate base. Or you can mix weak base and salt of its conjugate acid. Okay, so the example for number one is going to be mixing acetic acid, acetate, if you're creating this buffer solution, you can add you can mix acetic acid and salt of its conjugate base, right? So you will mix sodium acetate, okay? Or um, example of weak base and salt of its conjugate acid. Let's say you want to create a buffer solution where it has ammonium and ammonia buffer. In order to prepare this, you're going to mix ammonia and ammonium chloride. Okay, you're going to mix these two. You're going to mix these two to create the buffer solution. The second method to create a buffer solution is adding strong acid to partially neutralize a weak base, or adding strong base to partially neutralize a weak acid. Okay, so here's an example for the second method. For example, you want to make this buffer solution. This buffer solution can be created by mixing acetic acid and sodium hydroxide to create the acetated water. So the key point here is to add sodium hydroxide to the solution just enough to neutralize about half of the acetic acid, because you still want to have acetic acid in the buffer solution. You want to have half and half mixture of these, right? Key point. Add sodium hydroxide to solution just enough to neutralize about half of acetic acid, because you still want to have acetic acid in the buffer solution. Okay, so here are two methods, two ways to make a buffer solution. Okay, let me know if I have to go back.
Yes, please.
Okay. Let me know when you're done, okay?
All done.
All right. So here's how the buffer solution works. Let's say you have a buffer solution which contains weak acid, hydrofluoric acid, and fluoride, okay, conjugate base. The buffer solution contains equal amount of these concentrations. Okay, so if you add any substance with hydroxide, into this buffer mixture, if buffer solution, what's going to happen is the acid component will step up to react with this added hydroxide, which will cause slightly decreased concentration of the hydrofluoric acid, because hydrofluoric had to fight with this added hydroxide uh, ion. Okay, so what happens is the hydrofluoric acid concentration decrease slightly, and the result from this acid-base reaction will generate here hydrofluoric acid reacting with this added hydroxide anion, and it will generate the conjugate base and water, right? So now what happens is that concentration of this acid decreases slightly, and then you will have a slight increase of this conjugate base in the system, buffer system. Okay. In another case, to a buffer solution where you have equal concentration of acid and conjugate base, let's say you are adding a small amount of strong acid. You're adding a small amount of proton into this buffer mixture. What's going to happen is that the basic component will now step up to react with this newly added acidic component. Okay, so here, as you can see, the basic component is this conjugate base, right? this conjugate base is going to try to consume this newly added proton, and it will generate the hydrofluoric acid. So now what happens is that because this basic component had to step up and react with these newly added proton, the conjugate base concentration is going to decrease a little bit, but then this reaction produces hydrofluoric acid. So now the hydrofluoric acid concentration within the system is going to increase slightly a bit. So in this way, the system can maintain pretty stable and constant pH level throughout. Okay, the pH level will change, but it will not change dramatically. Okay, so this is how the system remains constant, stable pH level throughout. So how do we calculate pH of a buffer solution? Let's consider one example where a buffer solution made out of mixing weak acid uh, weak acid HA and one of its salts. Okay. The acid dissociation equilibrium in this buffer solution involves both acid and its conjugate base, which has an expression of so then the corresponding acid dissociation constant Ka expression is going to be product concentration divided by reactant concentration, right? So proton concentration times conjugate base concentration divided by initial acid concentration. So we know that since we know that negative log of proton is pH, right? If we take log on both sides, we are going to be able to find pH. Okay, so here what we did was you take negative log of both sides. You take negative log of Ka and take negative log of this entire thing. Okay, so if we separate negative log of proton concentration here, negative log of conjugate base divided by acid over here. So now what can you see? This is the pH, right? Negative log of proton is going to be okay. So then if you rearrange this equation and solve for pH, we have this expression. Okay, so then the pH of a buffer solution is basically pKa plus log of as the conjugate base concentration divided by acid concentration. This equation is known as the Henderson-Hasselbalch equation. You have to memorize this equation. So when we want to find pH of a buffer solution, we use Henderson-Hasselbalch equation. This equation only applies to buffer solution. Okay, so when we want to find pH of buffer solution, we use Henderson-Hasselbalch equation. Let's try this exercise.
Professor,
What
can
it,
you go back a bit? I'm sorry.
oh, sorry.
Okay, I got it. Thank you.
Okay, now let's try a sample exercise. What is the pH of a buffer that is 0.12 molar in lactic acid and 0.1 molar in sodium acetate? The Ka for lactic acid is already given. Okay, so then we're going to use the Henderson-Hasselbalch equation. This is not negative, so can you guys please delete this negative sign? Okay, so we're going to use the Henderson-Hasselbalch equation that we have just learned, and we just have to plug in all the information that's already given. Okay, concentration of acid is concentration of acid, concentration of conjugate base is already given in the question. Okay, so we plug in that. Ka value is also given. Okay, so if we plug in all these numerical value, the pH of this buffer solution is found to be 3.77. Okay, let's try another sample exercise. How many moles of ammonium chloride must be added to 2 liter of 0.1 molar ammonium? Ammonium chloride must be added to 2 liter of 0.1 molar ammonia to form a buffer whose pH is 9. Okay, and there's a note that's saying that assume that the addition of ammonium chloride does not change the volume of the total solution. Okay, so in this question, we're it looks like they're trying to prepare a buffer solution by mixing weak base and salt of ammonia's conjugate acid, right? So this buffer solution is made by weak base and mixing salt of uh, salt of conjugate acid. The weak base is ammonia. The salt of conjugate acid is ammonium chloride. So the base dissociation equilibrium in this buffer solution involves both base and conjugate acid. Let's write out the base dissociation reaction for this ammonia. So the base dissociation constant Kb is going to be ammonium times hydroxide concentration divided by ammonia concentration. Okay, water is not going to be included because it's uh, pure liquid. And the base dissociation constant for weak bases are listed in table 16.4. Okay, you can check that in chapter 16 lecture slide. This Kb information is found to be 1.8 times 10 to the negative 5. Okay, I'm going to make a note. Table 16.4, chapter 16, lecture slide. Okay. So the purpose of this exercise is to find moles of ammonium chloride, moles of ammonium. Oops. Okay, but if we want to find moles, we need to find the concentration of ammonium first. Okay, so we need to find the concentration of ammonium first. And it looks like from the Kb expression, we can easily find the ammonium concentration if we know the concentration of hydroxide and concentration of the ammonia, right? Since concentration of the ammonia is already given, we just have to find the concentration of the hydroxide. So let's try to find the concentration of the hydroxide. Since we are given the pH information, we can easily find the pOH. And therefore, from pOH, we can find the concentration of the hydroxide. Okay, so according to chapter 16, we already know that chapter 16, we already know that pH plus pOH equals pKw, which is 14, right? So then the pOH is going to be 14 minus pH. pH value is already given in the question. 14 minus 9 is going to be 5. Now that we have pOH information, we can use this to find the concentration of the hydroxide, which is going to be anti-log of this value. So then it's going to be 1 times 10 to the negative 5. Okay, so anti-log is basically 10 raised to the negative power of this value. Okay, that's the anti-log. Since we know all of the information we need, we can plug in these numbers into the equation and find for the concentration of the ammonium. Okay. The ammonium concentration is going to be Kb times which is 1.8 times 10 to the negative 5. The concentrations are already given, 0.1 molar divided by 1.0 times 10 to the negative 5 equals to 0.18 molar. All right, the concentration of ammonium is figured out, but then we need the answer in mole. Okay, let's convert this molarity into mole. Okay, mole of ammonium is basically going to be molarity times volume, right? 0.18. This is basically mole per liter. Mole per liter times the volume is given as 2.0 liter. Liter and liter cancels. You're going to be left with mole. The answer is 0.36 mole. This is going to be the final answer for the question. Does anyone need me to stop in the screen for a little while?
Yes.
Okay. Let me know when you guys are done.
Okay. I'm good.
All right, so every buffer has its own capacity. What's a buffer capacity refers to the amount of acid or base that a buffer solution can neutralize before the pH changes dramatically. Okay, that's the buffer capacity. If we use Henderson-Hasselbalch equation, the pH for buffer solution with 1 molar conjugate acid base pair equals to the buffer solution with 0.1 molar acid base pair. I'm going to elaborate that. Henderson-Hasselbalch equation is this. Okay, so for a buffer solution where acid concentration equals the conjugate base concentration, if acid value equals conjugate base concentration, this ratio is going to be 1. Log of 1 is 0. If this is 0, pH is basically going to be equal to pKa. Okay, so the pH is going to be same for the conjugate acid base pair of 1 molar of these or 0.1 molar of these. For example, if you are mixing, if you have a buffer solution of acetic acid and acetate conjugate acid base pair, let's say you have 1 mole of 1 mole of this, 1 mole of each in buffer solution versus 0.1 molar of conjugate acid, each an acid and conjugate base in the buffer solution. The ratio is still going to be 1, so then the pH is going to be equal to pKa. So in both cases, even though the molarity is different, these both buffer solutions will have pH equal to pKa, which is 4.74 for both situations. But however, buffer solution with 1 molar conjugate acid base pair contains higher concentration of acid and base, right? Higher concentration of acid and bases. So therefore, if we were to add sodium hydroxide into a buffer solution for an example, the buffer with higher concentration of acid, buffer with this 1 molar of acetic acid, buffer with higher concentration of acid will have higher capacity to neutralize this newly added sodium hydroxide base. Okay, so if we're adding sodium hydroxide, which one has better capacity? This buffer solution or this buffer solution? Of course, this buffer solution will have higher capacity to neutralize the newly added sodium hydroxide base. Okay, so the ability to neutralize newly added substance, the the capacity the capacity to neutralize newly added substance is called buffer capacity. So the
Sorry,
pH rate.
Professor.
Oh,
If
you
we
want me
go
to go
back
back?
real quick. Yeah. Okay, thank you.
So the pH range of any buffer is the pH range over which the buffer acts effectively. Effectively. The optimal pH where buffers most effectively resist change in pH in either direction is when concentration of weak acid and conjugate base are about the same. Okay, so in this situation, the buffer, uh, the buffer works most effectively. Okay, where the concentration of acid and conjugate base, concentration of weak acid and conjugate base are about the same, or when pH equals to pKa. Okay, so if the concentration of one component is 10 times more than the other, the buffering action is going to be poor. Okay, so an optimal buffer solution would have similar concentration of acid and conjugate base. Okay, similar good buffer solution or effective buffer solution will have similar concentration of acid and its conjugate base. Okay, this concentration doesn't have to be perfectly equal, but you want to keep this ratio close to 1 for an ideal better buffer solution. Okay, so therefore the pH range of pH range of buffer solution is going to be pH equals to pKa um, positive minus 1, close to. Uh, you want to keep this ratio close to 1. Okay, again, this is according to henderson hasselbalch equation. This component is going to be log of concentration of base over concentration, conjugate base over concentration of acid. Okay, so because you don't want this ratio to be too large, the pH, good buffer solution will have pH equals to pKa plus minus 1. Now let's take a closer look what actually happens when strong acid or strong base is added to a buffer solution. Okay, in previous slides we've learned that if you add strong base to a buffer, the acidic component will step up to react with the added hydroxide, right? Which will slightly change the pH of the buffer. If you add any strong acid to a buffer solution, the basic component within the buffer will step up to react with the newly added acid, which will also slightly change the pH of the buffer. So now that we have general idea of how this works, we will perform some actual mathematical calculations to calculate the pH of the buffer solution after adding strong acid or strong base. Okay. Adding strong acid or strong base to buffer will change pH of the buffer. Okay, we're going to calculate that. The first thing you need to keep in mind is that the addition of strong acid or base to a buffer solution, addition of strong acid or base to a buffer solution is a neutralization reaction. So we need to calculate like stoichiometry problem to find the concentration of acid and concentration of conjugate base when all of the added strong acid or strong base reacts. And then we use the Henderson-Hasselbalch equation to find the pH. Let's take a look at this diagram. It will make more sense. Let's say you have a buffer solution containing weak acid HA and conjugate base A minus. This buffer system has equal amount of acid and conjugate base. So let's say you're adding strong acid to this buffer solution. The newly added strong acid is a stranger. So then what happens is that the conjugate base component, this conjugate base component of the buffer will now fight against this stranger. The conjugate base will react with the newly added strong acid, and this reaction will produce extra acid HA. Now what happened to the system? Now the system has increased concentration of HA. With this HA, you now have additional HA from this reaction. So now the pH is changed. pH of this buffer system is changed due to the increased concentration of acidic component within the system. And in order to calculate the pH value, we need to calculate the new concentration of this acid and new concentration of this, because this was consumed, right? So we will calculate the new values of concentration of acid, concentration of conjugate base, and then we will use Henderson-Hasselbalch equation to find the pH value. Let's take a look at a situation where you're adding strong base. If you're adding strong base to a buffer solution, again, this newly added strong base is a stranger. Then what happens? The acid HA, the acidic component of the buffer, will now fight against this strong base, this stranger. Okay? The acid will consume this, react with the strong base, consume it, and get rid of it. So the reaction between acid and the newly added base will produce extra conjugate base. So now the system has increased concentration of conjugate base. You have this base plus this base. The pH of the system is now changed due to the increased concentration of the basic component within the system. And in order to calculate the new pH value, we also need to calculate new concentration of acid, new concentration of conjugate base, and then use the Henderson-Hasselbalch equation to find the pH value of the new system, newly developed system. Okay, we only have 5 minutes left. Okay, I'm going to end the lecture here. We're going to continue this next class. I'm going to hang around for another 5 to 10 minutes just in case anybody else has questions. Okay.